Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So the first paper this afternoon will be about variable focus video. It's a paper authored by Nitesh, Shroff, Ashok, Veeraraghavan, Rama, Chellappa, Yuichi, Taguchi, Oncel, Tuzel, and Amit, Agrawal, and Nitesh will be giving the presentation.
Hello. Hi, my name is Nitesh Shroff, and I'll be presenting our work on reconstructing depth and video for dynamic scenes. This is joint work with Rice University and Mitsubishi Electric Research Labs. Before I start the talk, let us quickly review depth from focus or depth from defocus. So it's a very well-studied problem for over a quarter century now. Here, given a static scene, you have certain focal setting, you take an image, you change the focal setting, you take another image, you change it further, and capture another image. So the focal stack thus captured is then fused to extract depth map information. And this uses blur as cue to estimate depth. And there are multiple advantages of depth from defocus over other depth map extraction algorithms. For instance, this is a passive method. You don't need any additional equipment, and the correspondence is obtained for free. But there is a big limitation. The limitation is that the scene has to be static while the images are being captured. A very, very related problem is that of the extended depth of field, where the goal is to have large range of depth in focus. Here again, you capture a focal stack and then pick pixels from image where it is sharpest. But here again, there is a big limitation of the static scene. So the goal of this paper is to extend depth from defocus and extended depth of field to dynamic scenes. But then the first question is, why do we care? So here is the commercial camera. We know all these commercial cameras have autofocus setting to it. But this autofocus setting is highly underutilized. And if you were to utilize it carefully, you could capture a video like this. Here you can observe the variation is due to two reasons. One is due to the motion in the scene, and another is the focal setting varies between two consecutive frames. And now, if we have this video and if we can extend depth from defocus or extended depth of field to dynamic scenes, what we can do is we can obtain a depth video and an all-focus video, both at 30 frames per second, from this captured video. So this is the motivation. So have I motivated you enough? Maybe not. So let's rewind 2 days back when Professor Srinagar presented this. And he motivated it very, very well. And I was definitely very motivated about this. And he used the quotation by John Steinbeck about the moment. And he talked about the duration focal stack, the moment focal stack, where he trades off the temporal resolution to maintain high spatial resolution. So basically what we are doing is just playing with the data he captures, and basically playing with the data that he has captured, and trying to create both a depth map video and an all-focus video. So this problem, as like other good problems, is challenging, because here the correspondence is lost because of the motion in the scene. And the motion in the scene could have been because of multiple objects, or could be due to the camera motion itself. And as we'll see further, the presence of blur makes the motion estimation even harder. So let us now analyze the effect of motion in depth from defocus. So here is a static scene, and here is the focal stack captured. On this focal stack, you can apply your favorite depth from defocus algorithm, and you'll extract a depth map with no correspondence artifact. But what if you had motion in the scene? If you blindly apply your depth from defocus algorithm on this, what you will obtain is correspondence artifacts. And here is the magnified version of the artifacts. You can see there are multiple copies of the wheel in the all-focus image that was obtained. So then the question is, how do we overcome this? Let's say somebody gave us the motion information. So the question is, how do we use this motion information? We can use this motion information to create a virtual focal stack. What we mean by this is, let's say the focal stack had 5 images. You can warp frames 2, 3, 4, and 5 to frame 1 to create a virtual focal stack like this. Or you could have warped frame 1, 3, 4, and 5 to frame 2 to create the second virtual focal stack. And now, if you apply your favorite DFD algorithm again, you will get nice depth maps. So what we have done is, we said if motion information is there, everything seems nice, life is good. But then the problem boils down to that of motion estimation. So you can see there are two images from the same focal stack. One is focused at the front on the train, and one is focused at the back. And you could see one point in the scene has red channel intensity value varying from 158 to 115, 43 intensity value change. So clearly, the brightness constant is violated, and this is the basic assumption behind optical flow estimation. So you can see this leads to spurious flow even in the static region. Even in the static region, you get around 2.5 pixels flow. So then the question is, okay, we want to estimate the optical flow between frame 1 and frame 5. So let's say somebody gave you the texture map and depth map for frame 5. What we could do is use the depth map to re-blur the texture map such that the focal setting of frame 1 and frame 5 matches. And then the optical flow will look nice because the brightness constant is satisfied. So now you can see the variation is probably 158 and 154. And hence, the optical flow is improved. In the static region, you have only 0.4 pixels flow. So in short, re-blurring improves flow estimation. So what we have done is basically created this chicken or egg problem. What we said was, if we have motion information, we can do well, we can get depth map. And then what we said was, if we have depth information, we could do well and obtain motion information. But then the question is, how do we estimate them? So one way would be a unified framework to solve motion and depth together, where we would want to solve multi-frame optical flow and multi-frame depth estimation together. But as you could guess, this would be a very hard optimization problem, and because of the large number of variables involved in this. Another nice way would be the iterative reconstruction, and this is the framework that we follow. We first capture a focal stack video. We first compute an initial optical flow. I'll come to the details of it. Use this optical flow to align images, and thus create virtual focal stacks. And then we can do depth map extraction on this virtual focal stack. And then once we have this, we can go back and refine our optical flow estimation. And once this converges, we'll have nice depth map and extended depth of field videos. So now looking at each of these blocks, so the optical flow block, in the first iteration, we don't have depth information. So the initial flow is going to be coarse. We could apply a few heuristic approaches or make assumptions about the scene. For instance, if you assume a constant velocity assumption between, let's say, let's say the focal stack has 5 images, you could compute optical flow between frame 1 and frame 6 because they are at the same blur level. And then if you could assume constant velocity, you can interpolate the motion between frame 1 and frame 2 using the motion between frame 1 and frame 6. But this is just coarse initial flow. And in the later iterations, we refine it and using the re-blurring approach that I just discussed. So this was the optical flow. So then is the depth map extraction and the extended depth of field image extraction. We create the virtual focal stack, and then texture map can be created using the photomontage algorithm proposed by Asim Agrawal in 2004. And for the depth map, you could pretty much use any off-the-shelf depth from defocus algorithm. Our formulation is based on the graph cut on superpixels, where the data term is reblurring term. Smoothness term is also between both the temporal smoothness and spatial smoothness. And here is the experimental prototype that we built in our lab. Instead of changing the focal setting, we move the sensor a bit, and this changes this changes a large amount of blur in the captured images, and here is a result on the CAN rolling data set. Here, if you were not to compensate for the motion, you can see you get a large amount of artifact in the texture map, and with motion compensation, the texture map is much better. And here is a captured video. This is how the captured video looks like, and this is the all-focus video. You can see some artifacts at the boundaries, and here is the depth map. I'll let it play once more. Here's the captured video, the all-focus video, and the depth map. Because we do not have the ground truth, so we can show this using novel view rendering results, and you can see it pretty much looks okay. And here is the result. Here's the result on another scene data set. And here is the scene with camera motion. You can see the camera is moving here, and this is the all-focus video created by this. And here is the depth map. You can see there is still artifacts on the boundaries, and the captured video again. And the depth map here. So this definitely has a lot of limitations still. It inherits limitations from the traditional depth from defocus algorithm, which is it needs scene texture, and then also from optical flow, where the motion between two images should be good enough so that the optical flow can still work. And it also has additional limitations in terms of the depth range of the scene, and the choice of initial flow estimation will introduce another extra limitations to the algorithm. In our future work, we are working currently on robustly reconstructing the boundaries and do better occlusion handling. In the paper, we discuss the occlusion handling also, and also characterize the fundamental trade-off in this scenario between the temporal resolution and the spatial resolution. So to summarize, in this talk, what we have tried to extend the depth from defocus to dynamic scenes. We carefully analyzed the effect of wedding blur in flow estimation. We proposed an iterative reconstruction algorithm using reblurring approach, and then we showed some results with experimental prototype. And the hope is that this will convert an off-the-shelf camera into a depth and video camera. Thank you for listening. I'll be happy to take questions.
We have time for questions? I'm curious if you get into trouble with the magnification that changes when you refocus. Do you have to do anything about this?
Yes, we do the homographic calibration. Yeah. Thank you.
All right. Thank you. The second talk is about depth-aware motion deblurring. It's work by Li Zhu and Jiaya, and Li will be presenting.
Thanks for the introduction. And in this talk, we're talking about depth-aware motion deblurring. The term motion deblurring used in our paper refers to the removal process to remove blur caused by camera shake. And this happens when you take images using handheld cameras and under dim light conditions. Recently, we have witnessed a rapid development in motion deblurring, and the methods can be generally classified into uniform and non-uniform approaches. And in today's morning's talk, there are very good papers and talks in today's morning session. And basically, the representative method assumes that the PSF is constant across the image, and all PSF is spatially smoothly varying in the image. So we discuss another problem in motion deblurring. We find that depth variation do affect the blur formation process. On the first place, scene points with different depths may have PSF changes, and the PSF change would vary. The scale of PSFs would change largely, evidenced by the point trajectory in the 3 patches. On the second hand, sharp depth discontinuity will cause abrupt PSF changes, and which makes it difficult to be estimated even use local patch-based methods. And this is one example. Using recent non-uniform and uniform deblurring methods, we cannot produce very good result. And the close-up shows that there still contains larger artifacts at phantoms. And this indicates that the depth variations in this example cannot be simply ignored. Actually, each point not only has a depth and also has a per depth PSFs to be estimated. So the solution space is very large. To this end, we tend to use an extra depth map to facilitate the PSF estimation. And we turn to the stereo camera solutions. This is because the stereo camera has a long history, and in last several years, 3D technologies has experienced a resurgence, and there are many commercial 3D digital cameras available on the market. And we use the Fujifilm Fine series, which can capture 2 high-resolution images at the same time, as shown on the right. So our framework like this. First, we take images using 3D cameras, and then use these 2 images to roughly compute the depth map. Further, we use this map to help PSF estimation in the hierarchical estimation schemes. And finally, we store the images. We find that even given a ground truth depth map, incorporating the depth into PSF estimation is not trivial, and we will show later. And our framework is an iterative process, and the obtained clear latent image can be further fed into the depth estimator to refine the depths and PSFs. We first see how we can establish correspondence between depths, between blurred frames. Tuzel Stereo told us that correspondence between 2 rectified images can be established using the epipolar geometry, and thus the disparity is in reverse proportion to the depth map, and it can be used to guide PSF estimation. When considering the blurred frames, if we assume that translational camera motion, that is, a camera undergoes translation motion, the correspondence between 2 blurred frames can be still established, and seen in this example. To obtain the coarse depth map is like this. It still contains many artifacts and is very coarse. This is because the depth boundaries may have occlusions, and blur also affect the depth estimation. However, the inaccurate boundary will not largely affect the PSF estimation in our hierarchical scheme, and the depths can be ameliorated to some extent using our obtained clear latent images. So now we see the major difficulties in incorporating the depth map into the PSF estimation and our hierarchical scheme. Given the depth map, a straightforward method is to apply the existing blind deconvolution methods to each depth layer. However, this is not easy. Taking this, for example, this region includes all pixels for 1 depth layer. By using our previous blind deconvolution methods, result is like this. The kernel contains obvious artifacts and is noisy, and the restored images have some raining artifacts. And this is explainable because the size of this region is not that large, and the small sized depth layer do not contain sufficient pixels for PSF estimation, and thus it fails most of existing deblurring approaches, I think. So we may consider that include more pixels for the blind deconvolution, and we apply the similar approaches and get a result like this. We can see that the PSF has been improved to some extent, and it is sparse and do not contain many noises. However, the restored images still have large draining artifacts. This might be because that it contains many pixels from different depth layers, and the restoration is not that easy. So what can we obtain accurate PSFs for small-sized depth region? That's our questions. And we use, interestingly, we find that if we can use the inaccurate PSF estimation as initialization, using the similar algorithms, we obtain a result like this. The kernel has been largely improved over the initializations, and the restored images is artifacts-free. So it reveals the two important factors of blind deconvolution. The first, we need large regions to collect sufficient pixels to perform a robust PSF estimation. And second, if we want to have a good PSFs for small-sized regions, we should have a good initialization. And these 2 points motivates our hierarchical estimation scheme based on a novel region tree. We see how we construct region trees based on the depth map. The depth map, we use in different color to label different regions, and notice that each region do not have a very large size. The number below indicate the disparity value. And then we merge regions with adjacent depth map or depth values to form larger regions for PSF estimation. And this process continues until we get sufficiently large regions for PSF estimation. And it has several advantages. Although each region has pixels with different depth values, depth variations will not be very large since we only merge adjacent depth values. And also, they are large enough. In this example, we have 3 region trees. And the PSF estimation is performed in a top-down fashion. For the root nodes in the region trees, we just estimate the PSF independently. For each levels in the region trees, the PSF estimation is performed in 2 steps. The first is the PSF computation, and using the PSF from the parent nodes as initialization. As we talked about that, the PSF initialization is very important. However, the PSFs might not always be improved because of the existence of textureless regions or noisy or very small size regions. So we should have refined these PSFs. And we call these PSF selections as we use information in the region trees to refine the PSF. The PSF computation step is similar to existing blind deconvolution methods, except that we use the examples from the 2 images and jointly estimate the kernel. Iterative operations and our closed-formed kernel solution is similar to our previous work. Now, given the computed PSF for each node, we need to identify the problematic PSF and then refine it. We use the PSF entropy to identify them because erroneous PSF usually contains noise and not that sparse compared to sparse motion kernels. Rather than simply dropping the kernels, we just use it to construct a PSF candidate set, and using these kernels and also the kernels from the parent and cell-brain nodes. And in this example, we have a kernel set containing 3 kernels. So the problem becomes to select one PSS from the PSF candidate set. And naturally, we can use a reconstructing error to select the correct kernels by measuring the residual errors between the reconstructed images and the blurred ones. However, it is known that such kind of reconstruction residual errors would favor a smooth interpretation, and thus smaller kernels will be selected. So we propose a novel shock filter invariance measures. This is based on correlation of 2 signals. One is a reconstructed images, and the other is a shock filtered version. Details on the shock filter invariance measures can be found in our paper, and here we only give some intuitive explanation. We show 2 signals. One is blurred and one is sharp, and the shock filter try to turn the blurred signals into a sharp one by finding the inflection point. And thus it alters the blurred signals a lot. So the correlation between the blurred signal and the shock filtered version is always smaller than the sharp sharp signals and its filtered version. And we can use the correlation to find the correct kernels. And in practice, we use the correlation of gradient magnitudes for the sake of robustness. We show some validation. Here are two patches, and we plotted it using a Gaussian kernel of size 5. And we computed the reconstruction error as well as our shock filter invariance measures. And the reconstruction error is plotted in the red line. We can see that they cannot find the correct kernel and always favor the smaller kernel size. And our shock filter invariance measures find the correct size. And by replacing the Gaussian kernel with the sparse motion kernels, we have obtained a similar result. And these are not two special cases. We have actually experimented with many patches and different kernels. And the experiments always suggest that our shock filter invariance measures outperform the classical reconstruction errors. So based on these PSF selections, we can find the correct PSF for each node. So at this stage, we have the PSFs and the depth maps. We need to reconstruct a clear image. However, the pixels near the depth discontinuities might not in compliance with the convolution model, so it might have some running artifacts. So we just increase the regularization weights near these depth boundaries. Using this depth map and the PSFs, we can reconstruct the final clear image. Our framework is an iterative one, and after we obtain the clear images, we can fed it into the depth estimator to refine the whole results. And we repeat this step twice. Now we see some results and comparisons. This is a typical reference image, and it's matching view. Note that the points at the far end is less blurred due to the distance. And this is our costly estimated depth and the region trees. By using the PSF estimated top level, we get a result image like this. Please notice the strong running artifacts on the cup and the box of milk. By propagating the kernels to the middle level, the results has been refined. We can further propagate the kernels to the bottom levels, and the quality of the images are getting better. This is a result from the first pass. And our second pass helps to further refine the result. The close-up shows that the second pass helps reduce the strong running artifacts in near textures. Another example, in our restored images, the characters on both foreground and background can be well recovered. This is a matching view, and the restored images of the matching view. We can notice that there are still some artifacts near the depth boundaries. And the depth map and PSF are shown here. The PSF suggests that the real blurriness actually varies for different depth depth layers. Finally, our method can be also applied to single image non-uniform deblurring by assuming that the PSFs now varies smoothly. This is done by just regularly partition images into 4 patches and construct a hierarchical estimation tree. Then the PSF is estimated in top-down fashion. This is the result, and the resulting PSF kernels, they do vary smoothly. And this is a blurred image from Joshi et al. From the graph. And our restored images, we can produce similar result to that in that paper. And this is a blurred image from Gupta et al., where cameras undergoes a translational motion. And our restored images. Close-up from different positions show that we can well recovered details at different positions. Finally, we conclude our work. In this paper, we have proposed a depth-aware deblurring framework And to our knowledge, it is the first attempt to incorporate depth into a blind deconvolution method. Currently, our method has some limitations. First, we only handle translation of camera motion. And maybe the further direction include extend current models to general non-blind, general non-uniform deblurring using the method of RIDE or the similar models like that, but it might involve much computations. So we learned from this project that PSF initialization is very important for blind deconvolution. And also, hierarchical estimation scheme is very useful for non-uniform deblurring, especially our region tree structures. Finally, the shock filter invariance measure always outperform the classical reconstruction errors. And that's it. Thank you very much.
We have time for questions?
Curious to know the sensitivity of this to noise.
You mean that?
The images that you're trying to blur are noisy.
And actually, we do not intentionally add some noise, but the images still contain some noise. And I think since we use samples from the true images, and the joint kernel estimation is a little robust to noise.
What about the step where you're computing that shock filter? That would presumably amplify noise a great deal.
Oh, you mean shock filter? Typically we can apply some smooth before the shock filters, but in this step we do not find the noise will largely affect the shock filters, especially in measuring our shock filter invariance measure.
I was curious if the variation of the PSF, is it usually due to depth of field effects? Or is it usually translations of the camera? I guess it's kind of the same.
Yeah, actually currently we handle the PSFs caused by camera motion, and it is sparse. So we just enforce some sparse priors to estimate kernel or something like that. But it can be extended to different blurs caused by focal blur.
Yeah, now that you have the depth map, it should.
Yeah. Yes.
All right, let's throw in the speaker again.
Oh, thanks.
All right, the last talk in the session is going to be about super resolution from internet scale scene matching. It's by Libin Sun and James Hayes, and Libin will be presenting the paper.
What did I do? All right. Can I use this mic? Or I guess I can use this. Yeah, I think that's, yeah, okay. Can you all hear me? All right, hi. My name is Libin Sun. I'm from Brown University. Today I'll be talking about super resolution from internet scale scene matching. This is joint work with James Hayes, my advisor. So before we even begin to the next slide, I want to make the distinction that the super resolution we're talking about right now is different from the one we've been hearing about in the past 2 days. So here we're concerned about upsampling a single image. So after downsampling the high resolution image, the high frequency information is lost. The only way you can sort of go from lower dimensionality to a higher dimensionality is by hallucinating possible details. And this is very different from sampling light field and then actually recovering the true high-frequency signals, right? However, this is a very well-defined problem, and there's a lot of paper on this. The image formation model goes like this. You start from a high-resolution image, apply Gaussian blur, downsample, add noise. Then you have the observation Y, which is a low-resolution input. And basically what we're trying to do is go backwards from the low-resolution image back to the high-resolution image. And here you want to have more pixels. That's the first thing you want to do. And then you want to also have sharp edges and possible details such as textures or object level details. So mathematically, this is definitely a very EO-posed problem. On top of that, there's this vision hard aspect about this problem that's very challenging. So for example, if I show you this low resolution image on the left, and ideally you want to go towards the right by considering all these high-level informations in the image that's very specific to the scene. You know, you want to insert snow, grass, mountain textures, and possibly, not textures from this indoor scene into that image. Now let's take a brief look at some of the previous work and see how people have been trying to tackle this hard problem. All right, so we argue that there are three aspects governing the quality of a single image super resolution algorithm. So the first one is faithfulness, is not in the plot, because this is basically capturing the image formation model, and this is relatively easy to satisfy by most of the algorithms nowadays. And on top of that, we claim that there should be two other things that we should look at. One is level of detail, which is on the x-axis. Then there's also realism. So an ideal algorithm should be on the top right corner, so far out there. So it's saying it should have a lot of details at the same time being realistic. And then you can perform very basic interpolation method that gives you minimum artifacts, but at the same time there's no detail synthesized at all. So this bicubic interpolation should be on the y-axis. And there are a lot of work on compact parametric models, such as gradient profile priors or sparsity priors, things like that. If you apply those, you can sort of restore the edges pretty well. It gives you sharp, clean edges. But these parametric models are very limited in terms of the way in terms of being expressive. It doesn't give you texture, which is a more complicated phenomenon. So there are a lot of data-driven and patch-based methods that try to hallucinate textures in smart ways. I won't go into detail into some of them, but I'll bring out a few very soon. So what we are trying to do here is basically build on existing method and try to expand the horizon a little bit and push the limit and see how far we can go in terms of inserting detail and at the same time being realistic. So, towards the other spectrum of the detail axes, you want to have sort of like object level details given the correct data and the algorithm. So if you look at textures and objects, these are very high, these carry very high information, high level information that sort of tells you if you can do some sort of recognition, you can sort of do the problem pretty well. And this has actually been tried by this paper from ICCP 2 years ago. So what they did is that they have a database of textures, and then they require this classification of textures first. However, this is a very hard problem. Given low resolution, you can't really recognize the material or the texture. So they require a human intervention to make sure the classification step is correct. And then after that, the synthesis step will be constrained, by drawing patches from only the relevant texture category. Another drawback of this method is that the texture database does not contain natural transitions between textures. This is very important because in a natural scene, these are some of the very salient boundaries in the scene, and they resort to a different pipeline to handle these edges and boundaries. Another state-of-the-art method comes from Sun and Tappan. This is 2 years ago from CVPR. So here they do not require any hard labeling of the or classification of the texture. Rather, they start from a input query image segment, and they find similar segment in a large database in terms of similar filter responses. So the hope is that by constraining the problem with similarly, contextually similar image segments, you can find similar patches there and hallucinate details that are appropriate. However, this doesn't always give you the correct, semantically correct segments. For example, if you look at the first row, it's very likely you will be inserting patches from ceramic plates into a zebra. This is not ideal, although sometimes visually you might think it's okay. So an ideal algorithm should really consider this high-level information, but it's very hard to do so given the low resolution. Other than these data-driven methods, there's also this body of work that focused on sort of this patch redundancy and self-similarity in natural images. This is a very interesting and very cool property of natural images. However, I guess there's sort of this inherent bound in like how much this can go, because they only resort to the patches available in the input image itself. So the signal present there is sort of limited, and there's probably some kind of upper bound towards how much you can insert. But nevertheless, they do. This is a very cool stream of work. So our work is sort of similar to some of the previous method in that we rely on external images, and we try to hallucinate details by drawing patches from other images. And the way we try to do it is by looking at scene matches. And the major contributions we claim are the first, so we're the first to consider using scene match for a single image super resolution. And we show that scene matching can be done reliably well at low resolution. And then this is a cool result. So we make a comparison to this CVPR paper last year, and we claim that scene match statistics can be favored over internal statistics, which is the opposite of the conclusion that that paper had. And finally, we want to say that we have competitive results, and we show that we can handle texture transitions really well beyond the capabilities of previous methods. This is just a brief overview of like how much data has been used in previous work. So for, I guess, the first seminal paper of data-driven single-image super-resolution came from Freeman, 2000. There were 6 images used. And towards the end of 2010, some of the state-of-the-art methods start to use more data to push the limit. And here we're considering internet-scale images of millions of internet-scale images. And the natural question you want to ask here is, how do you even leverage on so much data? Is it even doable? So we propose to use scene match sort of as a filtering step to filter out maybe like 99% of the images that are sort of irrelevant given this input image. So this is our pipeline. And let's talk about scene match first. All right, scene match sort of matured in recent years, and there has been a lot of papers in this field showing a lot of different applications. However, this idea of scene matching has not been sort of thoroughly explored in the context of super resolution. So we want to apply that and see how much we can do from there. So this is a very hard problem from the beginning because given these input images, so these input images are 128 pixels wide. These are really tiny, sort of like a thumbnail. And if you consider like the features you can extract from it, they're very limited, especially like texture regions. They're degraded by the downsampling step. So scene matching might be hard from here. But however, if you consider a combination of features, including global features, that sort of survive this downsampling step, combined with other low-level features, this is actually doable. And we show that given a large database of diverse scenes, you can actually find similar scenes. So on the right, we show some examples. We also show failure case in a later slide. So I guess these scene matches are reasonable, and they certainly give you some hope in terms of inserting details, because the textures you need on the left are available on the right. And on the right side, we have like a full resolution image. So we can build like a Gaussian pyramid and grab the relevant patch if you can find it. All right, so scene match is definitely one of the novelties in the pipeline. So why don't we, so I'm gonna spend some time sort of trying to get to the bottom of this and talk about the properties of scene match. So I wanna make a direct comparison to Zontag and Irani from CVPR 2011. Here we consider these properties, image statistics from different databases. There are 4 databases that we consider. The first one is on the left, that's the internal database. If you're familiar with this paper, it should be a very simple concept. But if you start from the ground truth image, suppose you have the input image with the high resolution ground truth. You form the Gaussian pyramid, so each database is a collection of patches, grayscale with mean removed. So you form the first one, which is internal database, all scales. You collect all the patches from the pyramid. That's your database. But in the context of super resolution, you only get to observe part of the pyramid, which is the lower frequencies. And from there, you get internal database limited. And then, same as that paper, we form the third database, which is basically images from the Berkeley segmentation database, you draw patches from those training images, and that gives you the third internal database. And for the fourth database, we're going to replace those BSD images with our C matches. So in our experiments, we're going to use 20 C matches for each input image. 20 is just the number we chose. We don't have a way to justify it, but it sort of works. And we're going to compare the properties of these four. So that CVPR paper actually claimed that internal database have a lot of desirable stable statistics behavior and should be favored over number 3. And what we're going to show is that number 4 is actually better, especially in the task for super resolution. So the first measurement we want to consider this quantity called expressiveness. So what does that mean, right? So first you choose your database, right? One of the 4. It's a collection of high-resolution patches. And then you start from the ground truth image, you pick a patch, and you ask the database, what's my nearest neighbor and what's my error in an SSD sense. And you do the same for all other patches, and you aggregate the results. So these two curves are from the internal database. The y-axis is the error, so lower is better. The x-axis is the mean gradient magnitude. So on the left, you have smooth ones. On the right, you have like sharp edges, and maybe in the middle, these are textures. So it's no surprise that internal all scales is a lower curve. However, this is dotted because they sort of don't participate in the competition because they capture much more than what you can observe in the super resolution scenario. So what's really competing is the solid red line. And this is by using 20 random BSD images. And this curve shows the 20 C match. It sort of wins marginally, but it's still rather a stable behavior. Now, another quantity you want to measure is called predictive power. So this is a little more complicated, but this is more consistent with the scenario of super resolution. So here, the database becomes a giant patch pairs of low and high resolution or frequency patches. You start from the low resolution observation, and you pick a patch, and you say, what are my nearest neighbors, and what's my estimation of the high resolution? So this is basically a weighted average of the corresponding high resolution patch. And you consider the difference between these estimated patch and the high resolution ground truth, and you record the error. And you do that for the other patches in the image, and then again, you plot these error against the mean gradient magnitude. So again, these are the internal database curves. This is where the BSD images are. And 20C match now becomes way lower than random images from Berkeley segmentation data. So this is saying if you have scene-specific data that are similar to your input, you can do a better job in terms of prediction, given a limited resolution image observation. So I guess that's a very cool property, and hopefully that'll give you this idea that it's promising to use scene matches for this problem. And now we're going to move on to the rest of the pipeline. So the rest of the pipeline are pretty much inspired by existing work. The next step we want to do is basically further constrain the problem by providing a region-level context. So we're going to do segmentation. And this is one example of the segmentation results. This is a very simple image. So you can see all the query segment on the left column, and then we show the top 5 segment matches. So one really cool properties of C-match is that textures co-occur in the C-match. So if you have sky against vegetation, chances are you can find similar boundaries or similar co-occurrence in the C-match. So what we're doing here is basically expand the mask a little bit in practice so that we can capture this fine transition between textures. And we have examples available for those patches. And we don't have to resort to like other pipelines to make this work. And then the heart of the algorithm is how we actually make use of these data, right? So the first step we take is sort of like a tiling process to synthesize possible texture over this image. And we take a greedy selection of pixel candidates. This is actually very similar to the single pass algorithm introduced by Freeman 2000 paper. And also, this is sort of like a standard practice in a lot of texture synthesis algorithm. So what's happening here is you pick a first patch based on the low resolution observation alone. You pick an example patch, and then you condition it on the existing high frequency patch. You will move on to make your subsequent choices. So there's this weak conditioning between the choice of patches. And after this tiling process, every location in the image has a number of pixel candidates, and we can plug in this nice energy minimization framework introduced by Sun and Tappan. So this energy function has 3 terms. The first one captures the formation model, saying it should be faithful. And then the second term is where the data come in. You want to say, my output pixel should be similar to one of the candidates, so that it's sort of natural and you can hallucinate textures. And then finally, we have a sparsity prior, sort of using student T distribution to make sure the image is heavy-tailed in terms of filter responses. And we run our experiments using a test set of 80 images of diverse photographic scenes. So we're going to look at some cool results. I guess I should turn off the lights. Just bear with me. Is it good looking? Okay. So we're going to show you 4 images on every slide. Top left corner is bicubic times 8 times upsampling in MATLAB. And then we show ours. So then Tappan is possibly the state-of-the-art method for data-driven methods that makes use of external database. And then Glassner et al. Is a very influential paper that sort of represents the best result from using internal database. So these make very cool comparisons. I'm going to show 3 close-up crops from each image, and you can sort of compare them and see which one you like better. So this is vegetation, and you can see some of the high-frequency details along the boundaries in our image. Does that look like water texture to you? A little bit. And then here, I guess those are like lily pads or something. I don't know. But hopefully that's sort of looking convincing to you. And this image is pretty cool because we have, in our C-match, we actually have basically a object level match. It's phone booth against sort of the same architecture in London, but not the same location. So given the correct data, we can actually produce very fine detail object level texture, for example, the corner of the bricks. And here, part of the phone booth, you can see sharp edges and more natural images. You can see transitions actually come out really well. Sky, vegetation, there's high frequency leaves there. You can see the grass along the boundary. And this is an interesting case where we have instance level scene match. So we have like photographs that are taken from a similar viewpoint of the same scene. You can see the rooftop sort of takes on a more well-defined structure compared to the others. All right, so I guess that's all the results I have. And I'm going to move on to some of the failure cases that could be interesting. So this is more intuitive, right? This is when you have bad scene match, it's like garbage in, garbage out. There's no hope of inserting useful textures. This happens quite a bit for indoor scenes. For outdoor scenes, we can do a pretty good job. And it sort of looks blurry, and straight lines are not well preserved. And this is, I think, the most interesting failure case. So this is not saying our C-match is bad. On the opposite, we have like perfect C-match. Like all the textures you need on the left can be found on the right. But the problem is the input image is not so structured. Like the tree trunk, that's the only main structure in the image. And it's just really hard for the algorithm to produce coherent textures. And this is what we get. It looks like a painting. You can sort of see like there are leaves coming out here and there, but they don't look great. So we think as texture transfer methods sort of mature or advance, we can improve the results even further. And finally, I'm going to talk about evaluation. So we did a perceptual study based on responses from 22 participants from our CS department, CS students. And here we show the charts by looking at two categories, right? So we have 10 test scenes, and 10 of them are sort of good scene with good scene match, and the other with sort of bad scene match. And it looks like, based on the votes we get, good scene matches actually produce way better results. So every time we ask the subject this question, which enhancement has better quality, and we're comparing against Sun and Tappan, because in a previous study we found that Glassner's result tend to have lower votes, so we ignored that. Every time we ask the binary question, which one has better quality, and the votes will be shown in the chart. And then for the bad scene match case, we're sort of doing a tie. It's not clear who's doing better. Yeah. So I guess that concludes everything I want to share with you. And just to reiterate, my conclusions are three. There are three conclusions we want to draw from the study. The first one is that we're the first one to apply scene matching to super resolution, and we show that it's actually reliably done. It can be reliably done. And then scene match statistics can be favored over internal statistics. So there could be nice properties that people can use for similar applications, maybe beyond super resolution. And then finally, we show good results, especially texture transitions, and our future work will sort of bring this further and make more realistic images. Yeah. Oh, yeah.
We have time for some question? Yes?
Yeah, it's the question actually I have more comments here. Is basically you started time frame from 2000. Actually, quite a lot of work was done in the 1990s.
Okay,
Yeah.
sorry.
So the problem with that. Basically, the external database used to call the VQ, right, vector condensation.
Okay,
Then the internal database, the whole fractal image was about. So
I see.
that's
Right.
the enhancement that they have quite a lot.
I see.
Much better.
I see.
So you may
I will look into that. Thank you very much.
Can you go back to the slide where you compared to internal versus external versus the four different methods?
Sure. Are you looking at expressiveness or predictive power?
Predictive error.
This slide?
Yeah.
Okay.
Both of them.
Mm-hmm.
So based on that, it looks like internal is actually worse than external, if I understand.
Right. Sure. So
Isn't that go against their results?
So yeah, one thing I want to mention is that for this experiment, we do not apply any transformation to any of the database. So in the Zontac paper, they claim that because for the internal case, you have very limited number of pixels. So to be more fair, you're going to apply a few transformations to them and keep the transformed patches in the database as well. So I guess in our version, it's a weaker version of the internal limited case.
So in that case, if you added the transformations back in as they did,
Mm-hmm.
I don't think it would change.
We actually have the plots, but I don't have them in the slides. We looked at it, and whatever the case, CMatch is doing better. So we apply transformations to all databases as well. We have a very large of transformations, including mirroring, contrast change, and very fine detailed rotations. And we apply that to all. Yeah.
Something you didn't mention is aliasing. If you're really at low resolution, you're not going to just see a blurry image, you're going to see a lot of aliasing. And I would guess that when you have a lot of aliasing, matching fails badly.
Yeah,
What happens then?
yeah, I understand. I guess this is something we haven't explored. So you're saying aliasing in the low resolution input?
That's right.
Right. So the hope is that these features that we extract will be robust enough to sort of sidestep those problems. I haven't looked into it, but I think it's a very relevant question. So I don't have a good answer right now. Yeah.
not sure I understand why you would have more aliasing at low resolution.
Well, if you capture an image at a certain resolution and you're looking at some part of it, it's very likely to have aliasing if that's zooming into a little piece of the image.
Well, it kind of depends on the ratio between your pre-filter and your sampling rate, right?
Right, but typically, I mean, for a typical camera, you can't assume that you don't have any aliasing showing up in the low resolution. I mean, that's, in some sense, that's the point of doing super resolution is in part to suppress aliasing, not just to scale an image up. So it's a realistic thing to have to worry about. What I noticed that the examples that he was showing, they all looked like the low resolution images were just small and blurry, but no aliasing artifacts at all, which is why I asked the question.
Right, I guess that depends on how the input image is formed, right?
Yeah.
So in this study, we don't claim to know how the image is formed other than the idea that there's this general image formation model, Gaussian blur, downsampling, add noise. Sometimes you are given an image that's low resolution and you had no idea how it's formed. And then from there, if you want to do upsampling, I guess sometimes you can't consider the image formation model like that. And also, like, so we consider times 8 super resolution just because this is actually a common amount. This amount of blur can be commonly observed in other scenarios such as defocus or motion blur. So it doesn't necessarily have to be super resolution. Yeah. Thanks.
All right, let's hang this speaker again.